Hi, this is János, it's Real Audio, and today we are starting out with something very special. It's Kintaro, introduction by Kintaro. Okay, so I think now he's ready to go and play with Sylvester. And just show him again. He's a huge cat. He's a very big cat, and he's purring. I have my microphone here. Not sure you can hear anything. Maybe, probably not. I can hear him. Okay, bye Kintaro. So today I'm going to show something really special. Let's get back to my screen. And you see I have some triodes for you. And we have here the smaller one. This is my 6J4 tube. From actually it's the 8532, which is the military variant, the US military variant of the 6J4, not 5-4, 6J4. And you see it in my Darlingham. So these are the tubes for the Darlingham. This is the input tube, which is a frame grid triode. So now I'm going to talk a little bit about triodes and show you triodes in operation. This is something that people don't really see big resolution, high resolution images of. Usually just see pictures of tube and that's it. But let's now click on it and see it in a little bigger format. So there we go. So this is a very small triode. Let's zoom in a little bit. And you can see that this is the central part of the tube. That's why they made, can you see, I hope you can see my pointer there. So this bit here that we see in the middle, that's why they made the tube. So the rest of it is just to house this part. And there are this layer up there which looks like a flat thing, like a waveform. And there's also like a lower platform, so like a lower platform and a higher platform. And these are usually, so it is not just this tube, but every vacuum tube has these things on the inside. So that's why I'm just going to show you two tubes, this being the driver tube, and I will show you the power tube. Both of them are triodes. And we are going to look at them on the inside. How do they look like? And what are the elements inside and what is their function and how the thing is put together. So basically you can see here, so this top part and the bottom part, these are the ones that space out the rest of the tube elements, the active elements, and don't let it touch the glass. And they make sure that the things don't rattle on the inside, but they are secured. And these are called the mica layers. And then there are like three different versions. Typically, tubes which have only a single mica layer, and there's some that have like double mica. So this has double mica layers, one on the top, one on the bottom. And there's some tubes which have like three mica layers. And of course, the more mica layers you have, the more it is secured in place. But I would say for this tube, as you see, the active element here, this is the plate structure. It's called the plate structure. It is really tiny, so the two mica layers are super close together, and and because of that tiny space, it doesn't really need three mica layers. Two are plenty. And as you see, it has these tiny feet that stick out from the mica. And these feet, there's a number of them. It's kind of like teeth sticking out. They are the ones, these teeth are the ones that actually touch the glass. Most of the mica, the rest of the mica doesn't touch the glass, because we want to make sure one thing, that the thing doesn't rattle on the inside. So these teeth are making sure it touches the glass, but you don't want it to touch the glass, the whole surface, because it can could pick up microphonics from the glass itself. So if when you tap on the glass, or the music makes the glass vibrate, you don't want those vibrations to be transferred to the plate structure. So what can we see here? And as you see, I have shown the photo from the side of this frame grid tube, and it's called the frame grid because the grid structure on the inside is not a spiral, which we will see in the next tube, but it's a frame, it's a metal frame. So this is a relatively newer development in vacuum tube production, that they actually use a metal frame for the grid. And the reason for that, for using such a solid grid, is that it allows much higher frequency operations. So I think this tube, it can operate maybe like 500 megahertz. So yes, this tube is linear from basically 0 hertz to 500 megahertz. So you can look for transistors that have such wide frequency range where they can operate. Anyway, so I just thought mentioning that that's why that was the advantage of this frame grid development, that it allows extremely high frequency operation. And of course they use this in applications such as radars and oscilloscopes. Yes, and as you can see here, you can see this part which glows like an orangey glow, and that is the cathode. And the cathode, that's the element which is heated. So that's in the core of every vacuum tube you will find a cathode. And when you have a direct heated triode, it means that the cathode is the same as the filament. And when you have an indirect heated triode, this is an indirect heated triode. So here there's the filament on the inside of the cathode. So the cathode is a tube, and the filament is on the inside. So the filament and the cathode has been separated. The filament is another name for the heater, which is essentially a wire. The heater is a wire that heats up. It's like a nichrome wire that you see in the toaster oven, that toasts your bread. It uses the same theory, same physics to warm up your vacuum tube. And here in this case, it warms it up just a tiny bit hotter than your toaster toasts your oven. I mean, not your oven, your bread. Because here in the case of these modern vacuum tubes, which are indirect heated and they have an oxide layer on the cathode, so these oxide type cathodes, they are heated to approximately 1000 degrees Celsius. So in general, I would say between 900 to 1100 degrees Celsius. And yeah, that's darn hot. It's super duper hot, a lot hotter than your toaster oven, and it's hot enough. Why do we need this heat? We need it to be so hot that basically this oxide layer is really close to melting, and we need to get it almost like close to melting, because in that state the electrons can be stripped from the cathode and they can fly towards the anode, towards the plate. The plate is another name for the anode. And here you see this thing on the outside, that is part of the plate structure. We cannot see. I will show the plate much better in my other tube, my bigger triode. So here this is just part of the plate structure. It's really odd, really open, kind of bizarre looking thing, and it's a little bit hard to see, but I thought that maybe we can just have a look at it. And look at that, in the bottom you can see this red thing, and nope, there's nothing glowing there. This is just the reflection from the glass, and actually the bottom of the cathode is also open towards the bottom, where the heater goes into the cathode, and from there's so much light coming out that it reflects from the base of the tube. So I think now that's it for our little triode, and now let's go for the power tube. So this is an indirect heated triode, and let's just see that this is the Darling Tubes triode, and it looks like a mini 300B, kind of similar to that. Now we can zoom in a lot, so now you will see things a lot cleaner, a lot clearer. As you see here, we also have some reflections from the cathode in the base, and this is actually part of the base. Let's see. So typically what we call as the base of the tube is you have that phenolic base that's on the outside of the tube, but that is something that they put on the tube after they made the vacuum on the inside, after the tube is ready. Then it, as an extra, the base is placed on the tube, and actually you can take off the base if you want to. It won't change the won't harm the tube if you now you can experiment with things like that. But anyway, so that's just the outer base of the tube. On the inside, you see this is like a piece of glass which embeds these rods. So there are these metallic rods embedded in this glass, so you see, and this is what supports the tube. So all of these rods will connect to the active parts of the vacuum tube, and on the inside you see something that looks like a funnel, and yes, that was a funnel. So this was the funnel, which was like an empty hole in the middle of the tube, and this is where the vacuum was sucked out. So that's how they suck out the vacuum, and now we cannot see because the base of the tube covers it. So that's where the vacuum pump is attached to, and once there's enough vacuum in the tube, then they melt the glass and just touch the molten pieces together, so the glass itself closes the vacuum, and the tube is ready to be finished. But that's the very last part of the production and manufacture of vacuum tube. So now we want to look into what are these rods doing, and as you see, these center ones, these two rods that are in this angle, these are the ones which are connected to the filament. And these center rods, they do not only support the plate structure that you can see. This thing is the plate structure in the middle of the tube. See that center, that's the plate structure. And these rods do the supporting, and in addition, they also go down to the tube base into the tube pins. So the connectors are, that's where these rods end inside your tube connectors. And most of them are electrical contacts, so they have a function, but often you will find some of them fulfilling a support role where they are just there to provide mechanical stability. For example, let's look at how they are. And in the middle you can see these two, so that I started to talk about. These ones are the filaments, the heaters, and you can see those tiny wires. And even there you can see that it's being wound around. There you can see it wound around that big support rod. Maybe let's go 200%. So you see it's threaded around it, and then it's welded on it. And the same thing for the other end of the filament, and then you see it goes into the cathode structure of the tube, and there you see that here we can see it on the bigger tube and higher magnification, that normally this is the outside, that's the cathode that you see, right? And on the inside, the filaments are a lot hotter than the cathode is, and then you see it's that bright yellow light. So the filament is really, really super duper hot, and hotter than the cathode itself, because it's just releasing the heat, and the cathode is picking up about 1,000 degrees Celsius from that heat that the filament or heater produces. And now you see that there is another support, that this one that goes on top there, and there another piece is welded to this support, and look at that. What's there? It's like a wire going around there, and there's another piece of wire which is not connected electrically to anything. And why is that? Because this is electrically the same potential as this support structure. So here we have these two wires inside the plate structure, and around these two wires we have a really thin wire wound in circle, and this thin wire, that's the grid, and these big poles are basically the poles to support the grid, and as you see down the grid, it looks like there. You see that it's soldered there, or I would say not soldered, welded. So these are things are always welded, and then it just goes, spirals up into the plate structure where you don't see it anymore. And what else can you see? We can see that here these two things, these were the heaters, and that one in the back, that goes to the back, and that's the cathode. So that's the cathode connection. So if this was a direct heated tube, there would be no cathode connection. And you would say that people say direct heated tubes sound better. Then why on earth did they make indirect heated tubes if it adds more complexity and it doesn't sound as good? And the reason for that is that for when you use an indirect heated tube, then the cathode is electrically separate from the heater. So it means that the filament itself, the heater, it runs on AC, alternating current, and when you have a direct heated tube, that adds hum to the sound. And when you have an indirect heated tube, then the cathode is at a different potential than your heaters, so there is no hum added. And of course, tubes are different. One indirect heated tube is different from another indirect heated tube, and yes, even for indirect heated tubes, let's look at like 12AX7 tube, which is like really popular tube. If you change your filaments to DC filaments, it quiets down the tube noticeably. So even though technically it's indirect heated, but yes, there's a little bit of capacitance between the cathode and the heater, and there's some hum being transmitted to it. And there are some other tubes which are much better resistant to the noise pickup from the filaments. And this tube, this power tube, the 1626, is an absolute king of rejecting any kind of filament noise, even though it has a 12-volt filament, 12.6-volt filament. So you would expect that you have to go DC filament for this power tube, and no, even with AC filament, if you run it and looking at its body, this is the body, the 8532 or 6J4. This is also an incredibly quiet indirect heated triode. So when you have an amplifier with these two tubes, if you like our darling amplifier, when we tried them out, both mine and Charlie's, when we tested them, we plugged it into the system and we thought that the amp is broken because it didn't make any noise at all, any hum. And even on Charlie's Edgar horns, we turned on his Darling amp, and I put my ear in the horn, and nothing. It's like over 100 dB efficient, and it flip the switch on, the power switch on, or flip it off. I couldn't notice any change between the two. It's so incredibly quiet. But this is an exceptional rarity. The vast majority of vacuum tubes, indirect heated ones, do have some little noise, and that's why you see that on the higher class vacuum tubes they always go for DC heated filaments. That's why, to keep the noise down. But if you know your vacuum tubes, you know which are the ones that do not require DC heated filaments, and the reason for that is usually if you can get by with AC heated filaments, the amp sounds more rich and more live. And for example, in the case of direct heated triodes, where you must direct heat them, when you go to DC filaments, then often that triode magic just goes away. So for tubes, heaters, filaments, and then how you run them, it's a very, very big issue. And let's go back to our big triode. Big. This is a less than 1 watt output triode. It has a 5 watt plate dissipation and approximately 0.75 watts output power in basically in class A. That's not very much, right? But it's a very clean output tube, and it sounds actually quite dynamic and quite powerful within the scope, within the range that you are using it for. And if you need more power than that, you can also use this as a very nice and potent and super quiet driver tube. So maybe you can use it to drive a 2A3 or a 45. Maybe you could try it to drive a 300B. Yeah. And so now let's have a look. So this is the plate structure, and there you see this plate is not just flat, but it looks like there's some dominoes on the inside, and they made the plate to have this shape and to give it rigidity so that it does not flex and doesn't warp. So it's really, really solid. And you see it's made of 2 pieces, one front side, back side. The 2 are here on the side. This is where they are held together, and you see those holes there. That's where they are crimped together, and so that it forms like a rigid one structure. So when they manufacture the tube, first they make the filaments, and then they place it inside the cathode structure. Then they build this the grid structure. Here we have the bottom layer, the bottom mica layer. Everything is fastened to that, and then they put the plate structure around this cathode grid filament structure, and they weld everything together. There's, you see, here's this additional thing. This is like supporting feet to make sure to keep the plate in position. Because as you see, that's one structure there, and we have it on the other side. That's the other support rod for the plate, but there's also these feet there that are making sure that the plate doesn't warp on the mica. And as you see there, you can see that it's welded there to the plate. There it's arc welded. They do a lot of arc welding during the making of a triode or pentode of any other vacuum tube. And you see on the top we have similar things. So these support rods reach beyond the mica layer, That's the support rods for the plate on the very side, and then you see here the support rods for the grid, and there the grid support rods are held together by a metal piece on the top to make sure that it doesn't move, doesn't warp. Everything is really solidly held together, and there you see in the center we have the cathode also fixed there. And guess what? This little tube, the darling tube, people are worried, and then usually there is a very bad misinformation that tubes have a very narrow frequency range and the transistors are so much better, and that's not actually reflecting reality, because this vacuum tube was designed to work up to about 50 megahertz. And yes, this thing is linear from DC to 50 megahertz. So most of the tubes, they have extremely wide frequency bandwidth. And the legend why people think they don't is because when you use transformers, the transformers often drastically limit the bandwidth of the tubes to a tiny fraction of what the tube is capable of. So in this case, like if you put on even like the best transformer, it's like 1,000 times less frequency range available than what you get, what the tube itself can do for you. And so that's why, for example, if you build a tube preamp with these two tubes, yes, this, and then you have maybe a capacitor coupling, there's no transformer output, then yes, you have to be very careful, because this preamp that you make from this tube will be operational up to 50 megahertz. So if you have some megahertz signals coming in or picked up through your interconnect, yeah, this preamp is going to amplify it faithfully for you. So, yep, so I think that was my introduction to vacuum tubes, and that's what they look like. This is what indirect heated triodes look like. And if you have any questions, just ask, fly it away. And that's it for now. Have an amazing day. And cheers, bye-bye.